Welcome to the massive open online course on Aspen Plus. In today's lecture, we shall perform another case study that is on production of cumene. Cumene is actually another name for isopropyl benzene, which can be synthesized through Friedel-Crafts alkylation reaction of benzene and propylene or propene. So this is the main reaction and the desired reaction, reaction number 1. And a parallel undesired reaction between cumene and propylene produces p-diisopropyl benzene. This one. This is undesired. So this is the desired reaction, this is the undesired reaction. The kinetics of the vapor phase isothermal reactor are given as follows. Here this is the activation energy, which is given in kilojoule per kilomole. These two things, it is activation energy. So this can be inserted at the proper place in Aspen Plus simulation window. Now the reactor is isothermal and it operates at the inlet temperature condition. That means whatever the temperature the feed material has, the reactor operates at that temperature only. Some more information we have about the process. We have two simultaneous streams of benzene and a mixture of propylene and butane. So we have one stream of benzene and another stream of propylene and butane. Okay, actually benzene and propylene, they react with each other, but butane is inert in this reaction. So the mixture contains propylene and butane in 7:3 ratio, and both the streams, they flow at 400 kilomole per hour, 20 degrees centigrade and 20 bar. So both of them, this is 400, this is 400. This is 20 degrees centigrade, this is also 20 degrees centigrade. This is 20 bar pressure, this is also 20 bar pressure. And they are mixed into a heater and the temperature rise is 350 degrees centigrade. So basically we have this benzene line, we have this propylene and butane line, which is 7:3 ratio. Both of them are 400 kilomole per hour, 20 degrees centigrade, 20 bar pressure. They are mixed and heated where there is a temperature rise of 350 degrees centigrade. So actually it becomes 350 plus 20, so 370 degrees centigrade around. Then one needs to evaluate the performance of PFR and CSTR to find out the better equipment for cumene production. So basically what we need to do, we need to employ a duplicator. Duplicator means it duplicates this stream and this stream as well, as if two same stream is going in different direction. Here we will put a PFR and here we will put a CSTR and do the simulation and check the better equipment for cumene production. The PFR dimension has been given. PFR is 5 meter long and 8 centimeter in diameter. It has 350 tube. So this is 5 meter length and 8 centimeter diameter, 350 tubes. So from this operation, we will identify the residence time, we will identify the temperature, etc. Those information will feed into the CSTR and then run both of them and check whichever is giving better production of cumene. And the subsequent run we will do on that particular reactor. So first we will do up to this point and check which reactor performs better. So for that, let us go to the simulation window. And one more information that we have to remember, we are supposed to use NRTL RK property method. Okay. So we have to add the components. First component is benzene, then propene or propylene, same thing, and they will produce cumene, very common component, so it will identify as isopropyl benzene, and butane, that is the inert, and the undesired product, which is p-diisopropyl benzene. So that we have to find diisopropyl benzene. I'm not writing the whole thing. Whichever the component contains this name, this part, we will choose from there. Yes, this is the one which we are looking for, p-diisopropyl benzene. So we add this. And we rename as p-diisopropyl benzene. Okay. Press next. And we press NRTL RK. Press next. Run. Okay, done. Now go to the simulation window. So we have to have one heater, one duplicator, one PFR. First, let us use these three and the feed lines. So we have one heater, one duplicator, and one PFR. Okay. So this is our heater. This is our duplicator. This is the PFR. Let us change the icon. This icon is not very good. So yeah, this icon is good. Now material in. So this is one material. It is benzene. And this is the combination of propene and butane. This will go to the duplicator. So duplicator will have one feed. This will be PFR out. Okay. Let us write here benzene or ben feed. And this one we can write other feed. This one is mixture. This one is PFR in, and this one is PFR out. So renaming is complete. Now we have to give the components. Benfeed input 20 degrees centigrade, 20 bar pressure, and benzene molar flow rate is 400 kilomole per hour. And then other feed, that is also 20 degrees centigrade, 20 bar pressure, and molar flow rate 400, but they are in 7:3 ratio for propylene and butane. So this is mole fraction 0.7 and butane 0.3. So we have 7:3 ratio of feed. Okay, then we have to give the specification of heater, which is temperature rise of 350 degrees centigrade. So we don't write temperature over here. Instead, we'll choose temperature change. So we have a temperature rise of 350 degrees centigrade. There is no pressure drop in the line, we'll assume, although it is not explicitly said in the statement, but we'll assume there is no pressure drop. And then there's a duplicator, nothing to fix over here, and we have PFR. PFR we have to fix first reactor type, reactor with specified temperature, and constant at inlet temperature. So that is what it has been said, that isothermal reactor at the inlet temperature condition. So it is inlet temperature condition. Configuration, we have to check what is the configuration. We have 5 meter long and 8 centimeter diameter. It has 350 tubes. So it is 5 meter long, diameter is 8 centimeter, and it's a multi-tube reactor with 350 number of tubes. And then we have to define the reactions. So set the reaction, which is a power law type, and go to the reaction set, new, okay, check the reactions. First is benzene plus propene produces cumene. So it is benzene plus propene gives cumene. So this is 1, this is 1, this is 1, it is exponent 1, it is exponent 1. This exponent is 0 because actually the reaction is equal to K into concentration of benzene into concentration of propene. It is 1 only, so we are not writing anything. But concentration of cumene is 0. That means this reaction rate does not depend upon the concentration of the product. So we do not write any exponent over there. Okay, so the first reaction is set, and the second reaction is we have cumene plus propene is diisopropyl benzene. So it is cumene plus propylene is this one. Here also -1, -1, 1, 1, and this is 1, exponent 0. So we have to write kinetic properties. It is a vapor phase reaction. And the first reaction we have ln K1 is 2.8 10 to the power 7. So the K value is 2.8 E7, and activation energy 104174 in kilojoule per kilomole. 104174. 104174 kilojoule per kilomole. And then second reaction, again it is vapor phase. K value is 2.32 10 to the power 9, 2.32 10 to the power 9, and E is equal to 146742. 146742 kilojoule per kilomole. So reaction is set and the whole system is set. Now run the system. Okay, so just go to the PFR result. So we have got a molar flow rate 69.933 kilomole of cumene has been produced, and this much of unreacted benzene and propene are there. Butane remains unreacted as expected because it is inert in this case, and a small amount of diisopropyl benzene also has been produced. Check the results. We have 367.786 degrees centigrade. Now one thing you should notice over here, that we were sending the feed as 20 degrees centigrade and they are coming to the heater. So the heater outlet should be 20 degrees centigrade, and in the PFR we have asked for 350 degrees centigrade delta T, the temperature rise, so it should come at 370 degrees centigrade. But here we find 367.786, slightly less than that. Why? Because of this mixing. Benzene and propene, butane, this combination, they are getting mixed over here. So the combined mixture is no longer at 20 degrees centigrade. It is coming below that. And as a result, with the temperature rise of 350, we are getting 367.786 degrees centigrade. This is the advantage of leaving certain calculations with Aspen. It will provide more realistic picture if it is allowed so. Okay. So we have this temperature. This is the heat duty. You can write it in kilowatt or megawatt. It is 1.9 megawatt heat duty. And the residence time is only 16.6706 seconds. Okay. And the stream results, already we know, this is the stream results. These are the stream results we have got. Okay. Now, go to the main flow sheet. We have to compare this with the performance of CSTR. So bring in a CSTR over here and attach the lines okay. So rename them. This is CSTR in, this is CSTR out, and this is CSTR. Keep it over here. And we have to fix the parameters of CSTR. Pressure, again, zero pressure drop. Temperature. We have to fix temperature. Unfortunately, we do not have any means to give the temperature rise. Otherwise, we could have given. So we just write the exact temperature which we know. It is 367.786 degrees centigrade. Valid phases vapor only. Specification type, reaction volume. But we do not have the information about the reaction volume over there as per the PFR combination. But one thing is sure, the PFR, we know the residence time. So what is the residence time of PFR? It is 16.6706 seconds. So the equivalent of residence time we will specify for CSTR also, which is 16.6706. 16.6706, yes. And the kinetics, already you have set R1 for PFR, the same R1 you can use for here, and all is set. Now run the simulation. Okay, now you can just go and check the results. We can add in CSTR out over here so that you can compare the PFR out and CSTR out side by side to check which one is better. So temperature and pressure, obviously there is no change because you have set it. And check the molar flow and mass flow. For PFR out, we have got a Cumene production of 69.933 kilomole per hour, whereas through CSTR you get around 9 kilomole per hour less. So we are at a disadvantageous position. So the amount of benzene unreacted and propene unreacted is naturally it is higher in CSTR. So in short, we will not use the CSTR. So the question that has been asked in the problem that is, evaluate the performance of PFR and CSTR to find out the better equipment for Cumene production. So without any doubt, we can say that PFR is a better equipment for this purpose, and we shall stick to it. Okay, we will stick to this one. Now we continue with the problem statement. So the outlet of the better reactor, so in this case it is PFR, is depressurized at 1.9 bar and 85 degrees centigrade before it is equilibrium distilled. So it is depressurized. So it was operating at 20 bar pressure. So we can use a valve for depressurization, or directly we can depressurize into a heater also, or cooler, that will serve the purpose. So let us go over here. So place one exchanger. This is heater 2. And this is H2 out. Okay. And this one depressurized to 85 degrees centigrade and 1.9 bar pressure. So run it, and we reach a value of, it is showing 2 bar because actually we can set the display with 1 digit after decimal point. So it will show 1.9 bar pressure, 85 degrees centigrade. What else? It is said it is equilibrium distilled in 20-stage column with total condenser, reflux ratio, reboiler duty. All this information have been given. The bottom product of the column is further equilibrium distilled in another column. There also the information has been given. So basically we need to have 2 distillation columns, one after another. So the first column, we use rad frac. So we connect this thing with this. Then one outlet. This outlet. So this one is column 1. What is H2 out? So the stream results, H2 out, you can check, 329.872 kilomole per hour of benzene, this much of propene, this is cumene, butane, and some amount of DIPV. Now here, even without distillation, if you analyze the vapor liquid equilibrium of these components, you can very well understand that the top product of the distillation column will mainly have benzene, propylene, and butane. And the bottom product will mainly have cumene and PDIPV. So these 2 will go mainly in the bottom, and these 3 will go to the top. Even in the bottom product, you may find some amount of benzene also. So among benzene and cumene, benzene will go at the top and cumene will go at the bottom. Let us check the columns one by one. So let us rename it as DIST and rename it as BOTT. And we have to give the information about column 1. So equilibrium based calculation, the number of stages we have 20 stage, out of which feed stage is 8th one. So we have 20 stages. The 5th stage is the 8th one. The condenser will be total condenser, and we have two informations over here. Reboiler duty 2 gigacalorie per hour and reflux ratio 0.5. So 2 gigacalorie per hour, reflux ratio 0.5. So reboiler duty 2 gigacalorie per hour and reflux ratio 0.5. And then pressure, I think the condenser pressure has been given. Yeah, 1.8 bar condenser pressure. So it is 1.8 bar of condenser pressure. Now it is ready to run. So run it and check the column results. Now see the column result. So check the distillate. We have almost equal amount of benzene and propene in the distillate. Almost no cumene over there. Butane, entire butane has gone to the distillate. And almost no DIPB is there in the distillate. Whereas in the bottom line, we have entire cumene, entire DIPB, and considerable amount of benzene. Now cumene is the product. Cumene is the main product in our system. So we have to separate this cumene from benzene. That is our goal. For that, we need a second column for distillation. Through this distillation, we expect cumene to be separated from benzene. So let us attach a second column. So press one second column over here. Attach this. This is column 2. Then this material out. This material out. And we will have mostly benzene over here, and we will have cumene over here. So we'll just write these names. Let us check whether we can separate benzene and cumene in this manner. Now, obviously, we have to give the parameters of column 2, which are available with us. So go back to the problem statement. We have 25 stages, out of which 13th stage is the feed stage. So we have 25 stages. The feed stream is 13th one. Condenser is total condenser. Again, the reboiler duty is 1.5 gigacalorie per hour and reflux ratio 0.6. So we have 1.5 gigacalorie per hour, and this is 0.6. Pressure 1.1 bar condenser pressure. So we have 1.1 bar. Now again, we are set to run. Okay, so the run is complete. We can check the results of column 2. And the results are available over here. See the stream results. Yeah. So you can check the Cumene line. Out of 68.4901, we have entirely Cumene over here. Okay, other things are very small amount. Benzene almost nil, butane almost nil, propene and PDIPB, anyway, they are not here in the Cumene line. But what about the benzene line? Again, benzene line will also have almost everything benzene except small quantity of Cumene that is going through the benzene line, and butane is almost nothing over here. So this is the difference between benzene line and Cumene line. So our target is to utilize this benzene, because benzene we cannot throw. Cumene line is, anyway, this is our product. So in the second column, the Cumene line is entirely Cumene, so this is our product. But this benzene line, we have to recycle. Okay, we have to recycle so that we can use up this benzene. For that, we have this strategy with us. Benzene is to be filtered from the vapor outlet of the second column through a membrane separator and recycled back to the feed line after necessary temperature and pressure correction. So what exactly we mean? We have this benzene line with us. So this one we will pass through a membrane separator where benzene will be separated from all others, and this benzene has to pass through some heater where temperature and pressure correction will be there, and that we can attach with the feed line so that this benzene can be reused in the system. So that's exactly what we are going to do in this line. Okay, so for that, let us bring a separator. So this is our separator, and we bring a exchanger. So this is our heater 3. This is our membrane separator. And we will have one mixer because we need a mixing line over here. Okay, so this is our mixer. This line has to be fed into the membrane separator. Then the outlet of the membrane separator will go to this line. Outlet of this will go to this one. One more outlet will go from here to here, that will be purged. Then this one will be reconnected with a new destination, which is this one, and this line will be connected to this. So we have our full strategy in this manner. Okay, we can just write this. Okay, fine. This name we can fix over here. Right. So we write it here as purge, and this is the purified benzene. This is the recycle stream, and this is the combined stream. Okay. We have to set the membrane separator where pure benzene will have 100% benzene, and the purge line will automatically be set. Heater will be used for pressure and temperature correction. So the temperature has to be 367.786 degrees centigrade. The pressure needs to be 20 bar. Now we run the system once again. So recycling is complete. Run it, and we pray that it converges. Yes, it is converged. So the temperature and pressure of the recycle line is same as the feed line. And the pressure, again, we have to give extra digit after the decimal point, otherwise we'll not be able to understand it properly. Yeah, it is 1.1 bar is the pressure. So the heater itself is working as a compressor and the heater, or else you can use a compressor and heater separately. Okay, so it can be purged this way. Now you check the cumene line once again, cumene and benzene lines. Okay, so go to the column 2, stream results. So the temperature of cumene line is 98.69. It is understandable because the bottom product is always at the higher temperature than the top product. The molar flow rates. Okay, so here we have a concern. You can check the cumene line. Earlier, without recycling, we had the cumene line with only cumene. But now you find that along with cumene, we have got extra 91.3034 kilomole per hour of benzene that is coming along with the cumene line. And benzene line relatively gets free. It is 145.857. Earlier, benzene line had benzene and some amount of cumene. Now, benzene line is free of cumene, free of propane, free of other things also. So earlier when there was no recycling, then entire benzene was going through this line and entire cumene was going through this line. But now, with the recycling on, only that amount of benzene is being recycled in this loop, which is useful. And rest of the benzene, which is coming into the system, is having only one outlet, that is over here. So this entire extra benzene is coming and coming out through this cumene line. In other words, this extra amount of benzene is not required in the system. we can very well reduce the supply of benzene, because unreacted benzene is being recycled. Or why to supply extra benzene in the line? So we want to reduce the benzene with an aim that we will increase the purity of cumene over here as much as possible. So we will supply only that much of benzene into the system which is required. In other words, we shall vary benzene feed and check the purity of cumene. Okay, we have to optimize the supply of benzene. So before optimization, you can do certain sensitivity analysis. What it does? Sensitivity analysis means you can check for various benzene feed what is the cumene purity. So you can check cumene purity against the benzene flow rate. So for 200 kilomole per hour benzene flow rate, what is the cumene purity? For 300 kilomole per hour, what is the benzene purity? And so on. And try to find out where exactly your optimized purity may lie. And then you can narrow down your range of optimization run. Okay. So for that, let us first take the help of the sensitivity analysis tool. So that will be obtained over here, model analysis tools, sensitivity, press new. Here, you have to vary the benzene flow rate in the feed. So it is the type mole flow, mole flow of what? Benzene feed, component benzene. Now, original flow is 400 kilomole per hour. So let us check between 250 to 500. It's a wild guess. You can increase the range, you can decrease the range also. Let us try between 250 and 500. And we will increment 10 kilomole per hour. So 250, then it will come 260, 270, etc. And then we will define two items. One is the cumene purity, and also we will identify cumene flow rate. Okay. What is cumene purity? Cumene purity is the mole fraction of cumene stream. What is the component? Component is cumene. And what is cum flow? Again, it is mole flow. Mole flow of cumene in the stream cumene. So do not get confused between the name cumene everywhere. Here we have given the name of the stream as cumene, and here cumene is the component. In the stream, this stream can be named anything, Q1, Q2, anything. I have given the name as cumene, so do not confuse between the component and the stream. And go to tabulate. Here you fill the variable of both cum and pure. And then you can run the sensitivity analysis. Okay, so it has successfully run. Just see the results. And here you find the result. As expected, at 400, your cumene flow rate is 69.9535 with a cumene purity of 0.43. And as you increase the feed rate of benzene, your cumene purity is going down and down. But look at the top. When you are sending very low flow rate, your cumene purity is 1, that is 100% pure. But in the bargain, your flow rate decreases. So up to 280 kilomole per hour, your purity of cumene is within the limit, and your flow rate is 68.954. Okay, so you can always argue that you do not want 100% pure cumene. 99.9% purity will be enough for you. Then you will arrive somewhere between 280 to 290, where this much of purity of cumene will be obtained. Okay. For instance, if you go to the simulation window and check, you can give the flow rate. Instead of 400, you give 280 kilomole per hour. And there is no requirement of sensitivity analysis tool over here, so just make it inactive. You do not want to do the sensitivity analysis now, so run. Okay, so when you run and check the results once again, you can check the column output. Yes. So now you check, you have got almost entire cumene with very less amount of benzene and very less amount of butane. Almost nothing is there. So your cumene is absolutely pure over here. And benzene line, obviously it will have the most, which will be purified. And in the bargain, you are losing 1.01 kilomole per hour of cumene through the purge, because this benzene line is passed through the membrane separation unit and pure benzene is being sent over here. Rest of the thing is purged. So cumene is being purged over here. So you are losing 1.01168 kilomole per hour of cumene through purge, but rest you can obtain. So without losing the quality of cumene, you can get the best output of benzene. And we do not have to do any optimization over here, because the sensitivity analysis itself will tell you where we need to stop. Okay, so we have performed the sensitivity analysis and optimized the quality of cumene production. So with that, we come to the end of this lecture and this case study. So in the next lecture, we will come with another interesting case study. Till then, thank you and goodbye.